Okay, I started out by doing the first problem, problem A. So we use formula A sub r equals v squared divided by r, and we plug our values in, we get 4.8 meters per second squared. So in order to have this acceleration, the component of the net force must be our formula right here, which is the forces. Sum of the forces, sub r is equal to m times a sub r is equal to m v squared divided by an r. The only force with a horizontal component is friction. So the sum of the forces, sub r is equal to sub s, which is equal to v m times v squared divided by r. So now we got to check to make sure that the maximum frictional force is not to be exceeded. We do that with our formula right here, which is F sub s is less than or equal to U sub s times the normal force. So since the normal force is N equals mg, since we I got this and I manipulated it to get both the masses to cancel. And it's going to leave us with v squared divided by r has to be less than or equal to mu sub s is times g. So the radial acceleration cannot exceed u sub sg, which is not plausible. And that limits the car to speeds which satisfy the formula, which velocity is less than or equal to the square root of mu sub s times g times r. So we use that same formula, we put all our values in for there, and we get that the velocity is less than or equal to 13 meters per second. And since 11 meters per second is less than the 13 meters per second, the car will not skid. So part B, what happens if the driver ignores the highway speed limit sign and travels at 18 meters per second? Well, at 18 meters per second, the car moves at a speed higher than the maximum safe speed, which is 13 meters per second, which we found here. So the frictional force cannot, safely help the car out. So the car will skid because of this. So C, what speed is safe for traveling around the curve if the surface is wet from a recent rainstorm? So it is so I got the limit of V is less than the square root of U sub s times G times R, and mu sub s is 0.5. So we use it and we plug in our values and we get that it is 11 meters per second. So now we can go to part D, which is for a car to safely navigate the curve at it is for a car to safely navigate the curve in icy conditions at the speeds of 13 meters per second, what banking angle would be required? And that would be so that we have to understand that the sum of the forces in the x direction equals n times sine of theta times mv squared divided by r, and then the sum of the forces in the y direction equals n times cosine theta minus mg equals 0. So we know that n sine theta divided by n cosine theta is going to equal tangent theta, which equals to mv squared divided by r divided by mg, which equals to v squared over rg. So to get the degrees, we do the inverse of tangent, which is v squared divided by rg, which is tangent, inverse of 13 meters per second squared divided by 25 times 9.8 meters per second squared, and that gives us 35 degrees.